Today, in this lecture, I will continue our discussion on eutectic systems in which the two components have a tendency to form a compound. There are two possibilities. The compound that is formed can be stable and show a congruent melting point, or the compound may exhibit incongruent melting point. The so-called, it may undergo peritectic reaction. And towards the end, I would like to tell you something about thermal analysis, a method that can be employed to study these types of systems. Let us look at the phase diagram showing the congruent melting point. For that, we must know what is congruent melting point. The two components of the system, if they react to form a compound, and compound that is formed if it has a mole ratio that is fixed, and if that compound can be heated so that it can be melted, and the melt formed has the same composition as that of the solid from which we started, such compounds are said to possess congruent melting points. And how they form the compound? If the two components have affinity for each other, they show the formation of a solid state compound, and as I told you, the compound formed will have a definite formula. Here you have a diagram which is representative of a system in which a compound C is formed between the components, and compound C has its own properties, it has its own melting point. And if you look at the diagram and you can recall what you have seen in the case of simple eutectic systems, the point here on the line corresponding to 100% A, that is pure A, gives us the melting point of component A, and similarly this gives you the melting point of component B. And when compared to that, compound C that is formed between A and B also has a melting point quite high. This system has lot of applications. Let us look at an example of a system which shows compound formation, and the compound has a congruent melting point. The compound that is formed between zinc and magnesium in the mole ratio 1:2 has the formula Mg(Zn) twice. Let us look at the phase diagram of it. The phase diagram gives us the line corresponding to the melting point of various compositions of components A and B, in this case zinc and magnesium. And if you trace the line from starting from the melting point of zinc and move along and finally reach the melting point of magnesium, passing through the melting point of the compound that is formed, that gives us the liquidus, because the system exists as a melt above this line. Similarly, if you start from the melting point of zinc and move along downwards and follow the line, below this line you have the system entirely in the solid state. Between these two we have the equilibrium between various solids that are present in the system and the melt. In the case of the region in which the melt is stable, where the two components, in this case magnesium and zinc, are completely miscible, is a bivariant system with F is equal to 2. And within these regions where melt and the solids are in equilibrium, we have F is equal to 1, that means systems are univariant. Since there are two eutectic solids formed, one eutectic is between magnesium and the compound, the other eutectic is between the compound and zinc. It is worthwhile to study the diagram and try to get the information what changes occur as we cool systems with different compositions. Start with a composition which is rich in zinc. We have mixed magnesium and zinc in the proportion corresponding to this line, this isopleth, and heat it to a temperature at which the system is in the molten state, and keeping the temperature at that point and then starting to cool the system along this line. The temperature decreases. We have sufficient number of degrees of freedom in this 2. We reach the point on the line here at which some solid appears. The solid that appears in this case is the compound MgZn twice. A small amount of solid appears and then the system is a 2-phase equilibrium, solid and the melt. We can continue cooling. The system will not resist because you are still left with 1 degree of freedom. As the temperature falls, more and more of compound is formed, and as the compound is formed, the composition of the melt starts drifting in this direction and finally reaches the eutectic point, at which the system becomes invariant because the curve corresponding to zinc intersects at the eutectic point. Now the system consists of 3 phases: the compound MgZn twice, melt, and then zinc has made its appearance. Because of that, the system becomes invariant. Whatever solidification that sets in, it takes place at constant temperature, and then ultimately when the entire melt has solidified, the temperature decreases and we are left with only solid phases. And you can see the solid phases that we have. In this case, the primary crystals of zinc Zn twice, which had time enough to grow from here to here, and then a solid that separated out corresponding to the eutectic composition, an intimate mixture of zinc and the magnesium Zn twice. So if you look at from the other end here, on the right hand side of the peak corresponding to the compound, similar changes can be brought about. Here again, the solid that separates out is the compound and melt is in equilibrium, and you are permitted to cool down the system. The melt composition drifts towards the other eutectic point, and then you will ultimately reach the temperature corresponding to the second eutectic point that is present in the system, and you have this, at which the system becomes invariant again. There is a temperature halt, but when the melt has completely disappeared from the scene, the temperature decreases. So you reach the region corresponding to the solid compound that is formed plus the eutectic. In this case, the eutectic is different from the eutectic formed in the earlier coolings. The eutectic here is corresponding to this composition. Now if you start on this isopleth, cooling this to start with F is equal to 2. In terms of phase rule language, F is equal to 2. The system becomes F is equal to 1. Cooling is allowed. Cooling continues, and more of solid, in this case magnesium, crystallizes out, and ultimately the temperature decreases. The melt composition drifts towards the eutectic point, and when you reach the line corresponding to the eutectic temperature, you will have an invariant system. 3 phases are in equilibrium. You have magnesium, the compound, and the melt, and solidification sets in, continues at constant temperature, and ultimately we reach a stage where the melt has completely solidified and we are left with only solids. What is the solid present here? We have magnesium and the eutectic, and which is the eutectic? Eutectic corresponding to this point. So you have now a clear idea about the changes that are possible along the isopleth when we start with different compositions. Now if we start exactly with this composition, what will happen? If you take zinc and magnesium in the proportion corresponding to the compound formation, as you heat it, such a solid, no liquid will appear till you reach the temperature corresponding to the maxima here, that is 590 degrees centigrade. Whereas if you start with any composition slightly to the left or to the right of it and heat it, in this case the moment you reach the line corresponding to the eutectic temperature, the liquid sets in, liquid is seen, the melting starts. slightly. Similarly, if you start with the composition on this side, again the melting begins at this point. The interpretation is not that easy. Is there a way out to make it slightly simpler? What do? You split the diagram into two parts, exactly bisecting it corresponding to the maximum in the curve. What is the result? You have two simple eutectic systems, and the interpretation of this you have seen earlier. It is easier than directly looking at the complicated diagram. How do you do it? You have now one solid here, which is the pure component. On the other end we have the compound, and it is a simple eutectic system to be interpreted, which is between one pure component and the compound, because compound itself behaves like an important solid like zinc and magnesium. It has its own melting point. And similarly, on this side we have a eutectic system, simple eutectic system between Mg(Zn) twice and Mg. How stable are the compounds that are formed? How do you get an idea? The appearance of the compound in the system is marked by the appearance of a maximum here, a peak. You have seen in the case of Mg(Zn) twice, peak is quite high, but if the compound is not that stable, height of the peak will be smaller. If it is less stable, smaller still, and ultimately the compound, if it is formed, may not be stable to reach the eutectic point itself. Therefore, in the case of systems, ultimately when the stability of the compound is in doubt, what result you get is a simple eutectic system. After having seen the phase diagram for a system showing congruent melting point, let us move on to the system in which the compound formed shows an incongruent melting point. What is incongruent melting point? The compound, if it is unstable, it cannot be heated to its melting point. Before that, it decomposes to give another solid having a composition different from the composition of the original compound. Then such a solid is said to possess an incongruent melting point. Here we can look at, we have a solid A, which when heated gives you solid B and melt, and solid B has a composition different from that of solid A. The solid B that is formed may be another compound or one of the pure components that is present in the system. A compound which is undergoing such a decomposition is said to undergo a peritectic reaction, and when the peritectic equilibrium is established, you can clearly see 1, 2 and 3 phases are together, which makes the number of degrees of freedom 0 and ultimately gives us a diagram which is different from the diagram that you saw in the earlier case. This part of the diagram is similar, but the compound that is formed cannot be taken above the temperature corresponding to this horizontal line. If it were stable, we could have traced the dotted line and gone to the point D here, which corresponds to the melting point of the compound. Unfortunately, the compound is not stable. Before reaching the melting point, it undergoes decomposition. It is said to undergo a peritectic reaction. In this particular case, the compound that is formed between the component A and component B, that is compound named D, decomposes to give solid B and the melt, and the point C is called the peritectic point, and the temperature corresponding to that is called the peritectic temperature. Similarly, in this case we have a eutectic point, the eutectic that is formed between component A and the compound. So, this part of the diagram is similar to what we have seen in the earlier case. What is need to be seen in this case is what happens if you take the mixtures of the two components corresponding to this particular composition, which is to the right of C. Although we have shown here, we will not study this. You can try on your own what must be happening when you cool a system corresponding to this point and move along the line to reach this, go below the solidus. Now, let us look at this cooling. You have a system which is rich in component B and you have small amount of A in it. You are in the melt region. The two components are completely miscible, F is equal to 2, and you cool it and you reach the point on the line at which solidification sets in. Our experience tells us that solid B separates out, and as you cool it, more and more of solid B separates out. In the process, as the temperature decreases, the melt composition starts drifting in this direction, and this continues till you reach the point on the line which is called corresponding to the peritectic temperature. And at this particular point C, the line corresponding to the compound intersects. That means it makes its appearance, the compound makes its appearance. The system becomes a three-phase system. Solid B, which was separating out in equilibrium with the melt, and the compound makes its appearance for the first time. Now it becomes a three-phase system and the system is invariant. The temperature becomes constant. It is the peritectic temperature, and now temperature can decrease only when one of the phases disappears. Now you have melt and solid, competition sets in, the reaction sets in, and in the process ultimately you have melt disappearing from the scene and you are left with only solids. When there are two solids, temperature can decrease and you enter a region in which we have solid B, which has time enough to grow, and then the compound D that is formed. Another cooling, now with the composition corresponding to this isopleth, nothing happens till you reach the point on the line. At this point a solid separates out. We know that the solid that separates out is solid B, and then we still have 1 degree of freedom. You cool the system, the composition drifts in this direction, you reach the peritectic temperature at which again you have a three-phase equilibrium where you have solid B plus melt plus the compound which has just made its appearance. Now again the three-phase equilibrium is there, you have no degree of freedom, the temperature becomes constant and cooling can take place only when one of the phases disappears. Now the reaction between the melt and solid B results in the complete disappearance of solid B, and you are left with compound C and the melt, and cooling will continue once the solid B has completely disappeared and you enter a region corresponding to compound D and the melt. It is the one with the degree of freedom F is equal to 1, and cooling can continue till you reach the point corresponding to the eutectic temperature, at which again there is a temperature halt and the system becomes invariant, and whatever solid that separates out below this ultimately when the melt disappears corresponds to the composition which is the eutectic composition, and you enter the region in which the compound that is formed while cooling from here to here, and then the eutectic that is formed from this point onwards. The eutectic itself is made up of two things, one solid A and compound which is an intimate mixture of the two, and you can clearly distinguish the compound that is formed initially while cooling from the peritectic temperature to the eutectic temperature and finer and uniform background in which the eutectic solid will be present. How to construct such phase diagrams? We have a thermal analysis method in which we study the cooling curves. In this case, we can look at the cooling curve for a pure compound. We take it to the molten state, and as a function of time measure the temperature, you can see clearly the cooling of the liquid, that is the melt, at which you have solidification that has taken place. This is called the initial solidification temperature. And then, as there are two phases in equilibrium and we lose the degree of freedom that we have, so the temperature remains constant as long as solid and liquid are present in equilibrium. And at this point, final solidification takes place and we are left with only solid which cools smoothly like this. But if you have a mixture, the cooling curve differs slightly. But if you take the eutectic mixture, where it behaves like a pure compound, it has its own melting point, sharp melting point, it will go a flat portion like a pure compound. Now, take a system in which we have two components. You can see number of degrees of freedom now is 2 for the melt, cooling is there. Now, there is an inflection, there is a break in the curve at which one of the component solidifies and the rate of cooling is slightly different now because the melt and a solid are cooling, and when you reach this temperature, the second component also crystallizes out, making the system a three-phase system. The temperature becomes constant because we do not have any degree of freedom left, and once both the solids have completely solidified, we regain 1 degree of freedom, the temperature can decrease. And we can use this to construct the phase diagram. The temperature of initial solidification is used to draw the liquidus, and the temperature of final solidification is used to draw the solidus. And the construction of the phase diagram from such cooling curves is called thermal analysis. Now, if you take a set of mixtures, the cooling curves are given here. This is for pure solid A, this is for pure solid B. So, you can trace this point and this point, and if you take various mixtures, you can get the point of initial solidification to have this point. Similarly, initial solidification, you can have a point on the curve, and in the case of mixtures, you will always see that you have the flat portion corresponding to the eutectic temperature. So, all will show this 1, 2, 3, whatever mixtures that you have taken. Ultimately, you are able to trace the curve corresponding to the melting points of solid A containing various amounts of solid B and solid B containing various amounts of solid A, ultimately meeting at the eutectic temperature. So, this must have given you some idea how to construct a phase diagram for a simple eutectic system. Let me summarize what we have seen today. We discussed about the eutectic systems in which there is compound formation. There are two types of compounds that are formed: the compounds that show congruent melting point and the compounds that show incongruent melting point. And finally, we looked at a method which can be used to construct the phase diagrams.